Okay, so picking up where we left off, we're going to talk about Dalton's Law of partial pressures. And just because I'm not sure if I pushed the button, are we really recording? Let's double check. Yes, we're really recording. Good. So, Dalton's Law of partial pressures is based on the fact that gases do not interact. And that's one of the things we said was the reasons why gases are easier, the reasons why gases can be described by PV equals nRT is because they don't react, meaning there's no intermolecular forces to worry about, at least initially. And now, we'll talk about what happens when we do consider the intermolecular forces, probably either at the very tail end of today's lecture or maybe at the beginning of tomorrow's lecture. And so, what this says is that in a pure mixture of gases, the total pressure is simply equal to the pressure of gas 1 plus the pressure of gas 2 plus the pressure of gas 3 at constant volume and temperature. So what this really implies is that gases mix perfectly. And so if we have a mixture of gases, then we can basically know everything about them and have everything be related to the amount of each gas in there. So we can also write that P1 is simply equal to chi1 times the pressure total. And chi1 is basically just a mole fraction. So it's defined as chi1 would be the moles of gas 1, oops, that's a 1, over the total number of moles. So if there's 5 moles total, and there's 2 moles of A and 3 moles of B, the mole fraction of A is simply XA equals 2/5, and the mole fraction of B is simply equal to 3/5. And so if we are given a mixture of gases and we know either all the partial pressures of the gases, or if we know the total pressure of the gases and the mole ratio of whatever we're given, we can calculate the pressure for any given thing. So an example of that might be relevant is we can come up with an example where we're diving. So let's say we're diving at a pressure of 8.83 atmospheres. Haley, off the top of your head, do you know how deep that is? Yeah, how deep it would be to be about 8.83 atmospheres? So, from diving class, I don't know this off the top of my head until I took the class either, it's about 33 feet for salt water is the equivalent of 1 atmosphere. So that means we're at a depth of about 260 feet, which is a pretty deep dive, right? With normal oxygen mixtures at 1 atmosphere, you can only go down to what, 60 feet, 70 feet really safely? So here you would need a different mixture. They call it nitrox. And so what we can do is we can figure out what that actual mixture should be if you wanted to go down to 260 feet deep. So we want the percentage of dive gas that should be O2 for the pressure of O2 to equal 0.21 atmospheres, which is what it is. This is the pressure normally. So the idea is that if you're down 8.3, well, if you're down 260 feet where the pressure is 8.83, we don't need as much oxygen in our mixture because we've got a higher pressure. And so what we end up with our dive gas is we end up with a dive gas that is much, much lower in pressure. So we can use that formula, which is basically that the pressure of any component of it is equal to the mole fraction of that component times the pressure total. And so we know that the total pressure at that depth is 8.83 atmospheres. We know we want the pressure of our oxygen to be 0.21 atmospheres. And so we simply solve for chi. And so what that says is that the partial pressure of, the partial pressure of oxygen that we want is 0.0238 atmospheres. And if we turn that into a percentage, so times 100 to get it to a percent, means we want our dive gas to be 2.83% oxygen. Compared to if we had our dive gas at normal atmospheric pressure, our dive gas should be 21% oxygen. And so if you go to this, you'll find that what they really end up doing is they make specialty dive gases with, depending upon the depths you're going to. And I really honestly don't know anything about diving beyond about 50 or 60 feet that we had in the scuba class, so I don't really know any more details. I did on the website put up a couple links to some interesting dive articles, I think, where they talk about some of the specialty dive mixes in there. But it's been a year or two since I bothered reading them. So this is important, of course, for diving, but it's also important for a lot of other things. For instance, if you go to the hospital and you get anesthesia, they want to make sure that they know the level of anesthesia in you, that they're pumping in versus the level of oxygen and various other things to make sure that that's correct. It's important for climbing mountains. For instance, if you climb Mount Everest, the last, I can't remember how many ever 100 feet, you basically need to take oxygen with you because the atmospheric pressure of oxygen is not enough for you to get enough oxygen, and you'll basically asphyxiate. Wait, does asphyxiate the loss of not having enough oxygen? Yeah. You'll basically asphyxiate within like 20 or 30 minutes or something ridiculous like that. And so you have to actually carry oxygen up so that you have a higher pressure of oxygen than what would be normal in the atmosphere at that level. It's just not enough oxygen for you to even survive. And it factors into things like figuring out the percent humidity in the weather and things like that. So this idea of using partial pressures for things is fairly widespread. Now, for chemistry, the closest example that we can find is kind of like doing humidity, in which if we have a reaction, like for instance magnesium solid plus 2HCl aqueous, that's going to produce magnesium chloride plus hydrogen gas. And the normal way we collect gas is we collect gas in a reaction by filtering it through water. Or if you think about it, because the reaction is also done in an aqueous environment, it means we have water. So if I had my beaker like this, here's my HCl. Of course, this is an aqueous solution, so there's water around. Then I have my little piece of magnesium. I, of course, have to put a cork in it, otherwise my gas all escapes. And what I do is I put a tube like this, and I collect the gas. But the problem is that I'm also collecting not only H2 gas, but water has vapor at that temperature too. So what I'm really collecting is a mixture of hydrogen gas and water gas. So for example, if I did the reaction at 20 degrees Celsius and the pressure of the atmosphere was 600 millimeters of mercury, and I collected a volume of 500 milliliters of gas, and remember that's H2 gas plus H2O gas, because we're doing the whole reaction in water, and water has its own vapor pressure at any given temperature. We would want to know is calculate how many moles of magnesium reacted. Now, the other way to do this reaction would be to simply measure how much magnesium is left over at the end of the reaction. And then measure how much, say, for instance, HCl has been reacted by doing a titration. But we can also collect the volume of gas. And so what we're really saying is solve for N in PV equals nRT. It's just that we have to realize that this P is equal to P of the H2 gas plus the pressure of H2O. So what that means is that if the pressure total is going to be equal to the pressure of hydrogen gas plus the pressure of the H2O gas, well, I know that this is 600 millimeters of mercury. And this we can look up. It is in Appendix E, which is page A20, and you would be given this on a test. Meaning, obviously, any giant tables of stuff, we never ask you to memorize it. And so the pressure of water at 20 degrees Celsius was equal to 17.54 millimeters of mercury. And so what that means is that we can solve for H2O by knowing this. Now this is kind of an easy example in that we can simply look up the pressure of the H2O to figure out the mole fraction. But it also is, you can do the exact same thing if you have a series of gases, or if you're given the mole fractions, it's just one more step. So that means that my pressure of H2 is really just 582 millimeters of mercury. And then, of course, the second part is kind of review. That's where we use our PV equals nRT. We decide that since I know PV and RT, I must be solving for N. And so we go ahead and say N is equal to PV over RT. Start plugging in all our numbers, 582 millimeters of mercury. Our volume, since our constants are in atmospheres, we have to do a quick conversion from millimeters of mercury to atmospheres. We put in our volume, 0.5 liters. We put in our gas constant. Oops. This is mole Kelvin all over 0.0821 liter atmospheres. So here's my P, these two parts. Here's my V. Here's my R. And for temperature, what did we say? 20 degrees Celsius, which is 293 K. And then what that leaves us with is moles of H2 gas. And so we do a little stoichiometry at the end. 1 mole of H2 gas, since this is moles of H2, is 1 mole of magnesium. And then we know that 1 mole of magnesium is 24.31 grams of magnesium. And so here we've got our mole-to-mole ratio, and here we've got our molecular weight. So one of the things we've been doing in Chapter 9 is we've actually been doing a good review of stuff we've learned in Chapter 4, meaning using mole-to-mole ratios and molecular weights. And so really what we're doing is saying anytime we deal with a gas, to calculate the information we need to know about it, we have to use PV equals nRT, and that if we're then, the rest of the reaction is either in solids or aqueous or something like that, we can use mole-to-mole ratios and molecular weights to figure out how much mass we have of something. If you plug this all into your calculator, you should get 0.387 grams of magnesium. So partial pressures are useful in a variety of things. We'll mostly use them as just a little extra part to throw on to a normal type of calculation that we're doing. So that brings us to our next topic, which is in section 9.6. It's called the kinetic molecular theory of gases. And what this is going to do is this is going to give us a picture and some more mathematics to understand gases. But the thing is that, it still predicts PV equals nRT. So PV equals nRT was basically based on observations only. So based on observations and measurements. But there's no real understanding. Meaning, we don't have a theory that describes it all. So this led to, in the early 19th century, two people named Boltzmann and Maxwell. And again, you don't have to memorize the dates. I just put it there for insight. Realize that we've always said that the understanding of gases is relatively easy because there's very little chemistry. And so notice that most of these discoveries are in the late 1800s, early 1900s. This is well before we had even discovered what an electron, a proton, and a neutron were. So these are basically observations that treat particles or atoms as simply small points. And they came up with this kinetic molecular theory of gas. So I call it KM theory because kinetic molecular is a lot of things to spell and write out. And basically what their premise was is that the properties of the gases can always be explained by the motion of individual atoms. And what they're really saying is that the motion is really just due to kinetic energy, and that we can therefore say the energy is equal to the work times the heat, just like we did at the very beginning of the chapter on thermodynamics. And they said that for this theory to work, there's 5 assumptions. And what we're going to find is that of the 5 assumptions, 4 of them are pretty darn good. And 1 of them is not perfect. And so when we always talk about the ideal gas law, what we're saying is that we're basing it on all of the assumptions being true, and then we'll look at what happens under what we call non-ideal situations, which is arguably what really happens in real life. So real life is not ideal, I guess. The first assumption is that gases are tiny particles. In constant motion. And we've already kind of looked at that. We said that when we were kind of defining pressure and we had a balloon, that the pressure was due to all of those particles bouncing off the balloon. The second assumption is something we've also mentioned, even though, like sometimes I really feel like we should just put 9.6 at the beginning of the chapter and just go on from there. But I just follow the book because that's easiest, I guess. And that is the fact that the volume of the particles is much, much less than the volume of the container. And we've said this before. What it's really saying is that gases are mostly empty space, especially compared to solids and liquids. And we kind of said this at the beginning, a gas is maybe at most 0.1% of it, whereas solids and liquids are on the order of 70% of the space is actually taken up by the atoms. The third one is that the particles act independently. And we said what this is really saying is that there's no attractive forces, meaning that intermolecular forces do not matter. And again, for the amount of kinetic energy in an average gas, that's very true, that there are no attractive forces between those molecules, or essentially no attractive forces. Now what we're going to find out is that's one of the ones that we kind of fudge for our definition of what an ideal gas is. And we know, if nothing else, that because eventually gases will condense down to form liquids, and then you can freeze a gas and form a solid, that there must be some intermolecular forces there. It's just that the kinetic energy the particles have in the gas state is so much larger than the intermolecular forces that we don't see those intermolecular forces as having very much of a role generally. The fourth one is that all collisions are elastic. And what that means is that there's no loss of energy. And therefore, the total kinetic energy is a constant. And then the last one is that we can describe the average kinetic energy as being proportional to the temperature. So one of the things that I talk about, or that I kind of fudge when I'm, especially in my other classes, I always tell people that temperature and energy are the same thing, that the higher the temperature, the more energy you have. And that's true, but they're not really the same thing. What temperature is describing is the average kinetic energy. And we'll draw some graphs later on and show that even though we talk about the average kinetic energy, we have to remember that some particles have above average kinetic energy. And in fact, that's what we used as our explanation for vapor pressure in Chapter 10. So we'll revisit that. And since Chapter 9 and Chapter 10 are on the same test, the order that we covered in doesn't make a whole lot of difference. And so what this is saying is that kinetic energy is equal to 1/2 mv squared, where since we're talking about the averages, we need to put these little bars over them. So the bar is essentially saying that we have the average. And so remember, some particles can be above average, and of course some particles are below average, much like anything else in life. Now what that means is that using rules 1 through 5, we should be able to explain all properties of gases. So for example, if I look at, say, property A, since I don't want to use the numbers 1 through 5 since it gets confusing to have too many numbers, we know that gases are compressible. And if you look at that, that's essentially due to what we called rule number 2, that gases are empty space. And you can also argue that it's also a little bit due to the rule on intermolecular forces, which says that they're not important because for a solid and a liquid, the reason we can't compress them any further is that first off, they're about as compressed as they can possibly get at about 70%. And second off, because the intermolecular forces are attractive forces, but we know that if we push two atoms too close together, that the repulsions from electron-electron repulsions will push them out. And so solids and liquids are kind of at that limit. We know also from our observations of gases, and this is even going back to Chapter 1, that gases always fill their container. And in Chapter 1, when we were sort of talking about solids, liquids, and gases, and I forget, it might be Chapter 2 in your book, I forget which class I'm teaching sometimes, what we're really saying is that they have indefinite shape and indefinite volume, meaning gases can have any shape, they'll fill any container, any room, and they have an indefinite volume, meaning if you've got a little container, you can put gas in it, and if you have a big container, the gas molecules will be equally spread out, as opposed to, say, a liquid that certainly will take on the partial shape of the container, but will only fill a very specific volume of that container. And again, that's essentially rule number 1 and rule number 3, where rule number 1 is that the molecules are constantly in motion. So that's how they can fill a container. And then rule 3 simply says is that they're independent of each other. So if you think about it, if I have a container like this filled with liquid, the liquid just stays at the bottom. That's because a liquid obeys rule 1, meaning the particles are constantly in motion, but it fails rule 3 because there's intermolecular forces holding them together. Whereas a gas, because it has those rules, and of course for a gas we better put a stopper in it, we know that the molecules can be anywhere we want them to be and moving in any direction because they're constantly in motion, and the fact that they're independent of each other means they don't clump up at the bottom or in a corner of the container at all. Okay, the next set of rules are simply the ones we already know. For instance, Boyle's law, which says simply that pressure is proportional to volume at constant temperature and pressure, constant temperature and number of atoms. And if you think about it, this one can be explained is that we know that the gas pressure is due to the particles hitting the sides of the container. Therefore, if I decrease the volume, that means it leads to an increase in the number of collisions. And so that's using our kinetic molecular theory of gases, saying that it's the collisions that matter, that's what, and that they're elastic. Therefore, we have to increase pressure. And of course, the next one after Boyle's is simply Charles' law. And that's the one that says volume is proportional to temperature at constant P and N. And this is essentially due to Rule 5, which says that kinetic energy is proportional to temperature. So if we take a look at it, if I increase the temperature, that's the same thing as saying I increase the kinetic energy via Rule 5. That means I'm going to increase the number of collisions because I have more kinetic energy, and I increase the force of the collisions. Therefore, if pressure is constant, the volume of the container has to increase. The container, has to increase, there we go, in order, or so that, I guess, I like that phrasing better, so that the number of collisions decreases for pressure to be a constant. So again, all those laws are good, and they were very easy to observe because gases obey pretty easy and simple laws, and they were observed well before we even knew about atoms, molecules, protons, neutrons, electrons, and things like that. But the nice thing about this law is that once we establish a mathematical, some equations to it, especially part 5 where we're talking about the kinetic energy, that allows us to do a lot of other calculations on gases that we wouldn't necessarily know how to do. Okay, we can also explain Avogadro's law. He said that the volume is proportional to the number of atoms at constant temperature and pressure. And this is basically just rule number 3, which says that the molecules are independent. Therefore, if I increase the number of molecules, that means that I increase the number of collisions, which leads to a corresponding increase in pressure. But if pressure is constant, then I have to increase the volume to decrease the number of collisions. And so we can see that that's true. And then, of course, the last thing we talked about was what we first started with today, which is Dalton's Law of partial pressures. And when we were talking about Dalton's Law, we said that basically this is true simply because the gas molecules are independent. That's rule 3. Therefore, they do not interact and therefore mix perfectly. We know that if we take two solids and mix them up, that they don't tend to mix unless you're melting them to a liquid first. We know that there are plenty of liquids like oil and water that we can, put in the same test tube, shake it up all we want, and they're going to separate out into oil and water, just like salad dressing does if you let it sit on the shelf too long. But gases, once they're mixed perfectly forever, and you can't separate them, at least not very easily. Okay, so we can do some mathematics now. If we know that the kinetic energy of the gases is equal to 1/2 mv squared, then we also know, and we're not going to bother deriving it mostly because it's like 50 steps, is that that's 3RT all over 2 Na, where Na is just a fancy way of saying Avogadro's number. So what we're saying is that if we can figure out, if we know the kinetic energy of each individual particle, then the total kinetic energy, of course, depends on the total number of particles. That's why Avogadro's number pops up there. And that's simply related to the gas constant R and the temperature. And what that allows us to do is we can solve the equation for V, which remember is the average speed. And so V average is simply equal to the square root of 3RT all over m Na. And remember, mass, that's the mass, that's Avogadro's number. What that ends up being is simply the molecular weight, and so we can also say it's equal to the square root of 3RT all over m, where m is in grams per mole, it's our molecular weight, and temperature is of course in Kelvin, and R is our friendly old gas constant, except since we're talking in terms of energy, we want to use 8.314 joules per mole K. And what this simply says then is a couple simple things, that light molecules move fast, heavy molecules move slower. Or that what that's saying is that the velocity, or the average speed, I should say, not velocity, the average speed of those molecules is simply inversely proportional to the molecular weight of it. So inversely proportional. And it also allows us to do some calculations. For instance, if I wanted to calculate the average velocity of a helium molecule, well, I know it's 3. I know that it's R, 8.314 joules per mole Kelvin. And we'll say that we're at room temperature. So that's 293 Kelvin. And then for the molecular weight, we know that there's 4 grams of helium per 1 mole. And then if we take a look at our units, my moles cancel, but I've still got the joules, Kelvin, and, Kelvin cancels. I was going to say it better cancel. We've still got joules and grams, and we know that 1 joule second is equal to a kilogram meter squared. That's our definition of a joule. And so notice that then I can get rid of my seconds squared. I can get rid of my joules. And then the last step is I've got to go and convert between grams and kilograms. So now I can get rid of my kilograms and my grams. And so notice that the only units I'm left with are meters squared and seconds squared, which is good because I have to take the square root of that whole thing. And so if I take the square root of those units, that gives me meters per second, which is exactly what we would expect for the units of average speed. Taking square roots in a bar problem is kind of strange, so I usually just do the actual bar problem, keep track of all my units, and then you can either put a giant square root symbol in it or parentheses with the power to the 1/2. And so that ends up being about 1.36 times 10 to the third meters per second, or if we do a little bit more work that we're not going to bother showing you, it's about 3,000 miles per hour. And certainly you guys are capable of converting meters to miles and seconds to hours by now. So if you think about it, that little helium atom is booking. 3,000 miles per hour means that it can go from New York to LA in an hour. I wish I could go from New York to LA in an hour. That'd be pretty cool. Now, we have to put a couple caveats. And so we have to remember that, again, this is our average. Whoops, I forgot the little average symbol. This is our average speed. So there's molecules that go faster and there's molecules that go slower. And also that this ignores collisions. So this is saying that if I had a complete vacuum from here to the other side of the country, then I shoved the little helium atom going its average speed in that direction, it'd take an hour. Or it would go 3,000 miles every hour that I let it go. But we know that we don't have a vacuum around here. We know that, for instance, there's a lot of gas molecules. And so what happens is that since it does a lot of collisions, that means it actually follows a zigzag path. And so what we're saying is here's our little helium atom, and that because it's crowded out here, the helium is zigzagging off different molecules, and so it's never going in a straight line. In fact, if we look at it, the average distance that it travels before changing directions is only 2 times 10 to the minus 7 meters. Now, if you think about it, that's about 100 or 200 atoms wide, or distance. So that means that basically it's crashing into an atom quite frequently. And that tells us that the number of collisions per second, if we do the calculation, is 10 to the 10th. Now, we're not doing any of those. We just want to kind of have a feel for this. So what we're saying is that that helium molecule is never going in a straight line, and it's always hitting other molecules. In fact, it's hitting 10 times 10 to the 10th. That's over 1 billion molecules every second. So that little helium atom is mostly bouncing around in no given direction and not moving very far out. Now we know that, for instance, they must be able to go a certain distance in a specific direction. That's due to something called Brownian motion. But we also know that, for instance, if I just open up a bottle of perfume here, then eventually Haley, way back there in the back of the classroom, can smell it, right? And so we know that at some point, it has to diffuse outward. To give a scale, and this is in your book, helium is about 1.36 times 10 to the 3rd meters per second. And if we take a look at hydrogen, hydrogen's of course lighter, so we expect its velocity to be larger. It's about 1.960 times 10 to the 3rd meters per second. Versus, say, water, so this is 4 grams per mole. This is 2 grams per mole because it's a diatomic. Water is about 18 grams per mole. And that only has an average speed of 650 meters per second. Oxygen, which is 32 grams per mole, only has a speed of about 490 meters per second. So as mass increases, so does the average speed, which is what we said earlier when we looked at the equation, meaning they're inversely proportional to each other. There's 2 good pictures that I like. There's the corresponding pictures in your book, but I'll sketch them up here. This is essentially figure 9.12, and what we're sketching is this idea that at different temperatures we have different average speeds. So if we look at the percentage or the number of molecules with a specific speed, and we take a look at the average speed in meters per second, then what we find is that at low temperatures the molecules aren't moving very fast, but some of them are moving fast. So this would say be 100 Kelvin. And that as temperature increases, so does our average speed, but because the number of molecules is supposed to stay consistent, which there's no way I can sketch a good graph of that part, that both our average speed increases. So as we increase the temperature, our average speed increases, but the distribution widens. So at very low temperatures, most of the molecules really are going the average speed. But by the time we're even at 300 K, there's a significant number of molecules that are going faster than average and a significant number of molecules that are going slower than average. And then, that trend continues. If I go all the way out here to 700 K, I've got the average speed might be, some value, but a significant portion of the molecules are going nowhere near the actual average speed. So one of the reasons you have to be careful with averages. Haley, did you take Math 120 or are you taking 121 right now? Has Garth talked about mean and averages? A little bit. One of the things that always bugs me in life, for instance, is if you say the average salary of an American is, say, $40,000, right? That's wonderful, but but that's the average, including all the billionaires and trillionaires and things like that, and all the people who make no money. So that average almost means nothing. What's more important is what is the mean salary, meaning what is, when you factor in the people making billions, what does most people make? And what most people make is less than 40,000. So one always has to be careful when one is talking about averages versus means. For instance, when we talk about the average speed of a molecule, well, not very many molecules are actually going that average speed at very high temperatures. The other graph that sort of illustrates this, and I'm not sure if this was in your book, I don't think it is, that I think is kind of interesting is if I take a look at the number of molecules versus the speed, and we change it as a function of molecular weight. So notice that the idea is that this graph is mostly the same as that other graph, that for instance here's chlorine at 70.9 grams per mole, and most of its molecules are going to go very slowly compared to, say, nitrogen, which has got 28 grams per mole. And of course, if we take a look at our speedy guy, helium, he's going to have the highest average speed at 4.0 grams per mole. But also notice that there's a pretty good distribution of speed, meaning a lot of helium atoms are actually moving faster than average, whereas a lot of helium atoms are also moving slower than that average. Whereas for something that's higher, like chlorine, then we expect it to, kind of bunch together pretty much. And so what that means is that basically lighter molecules move faster to have the same kinetic energy. And it also explains, for instance, why there's no helium on Earth. Well, exists in Earth's atmosphere. We should actually rephrase that. I'm not saying helium doesn't exist on Earth. I'm saying it doesn't exist in its free form in the atmosphere. Because if we take a look at the average speeds and we plot it, well, right here, this is what we call escape velocity. And what that simply says is that any molecule with greater than this velocity will eventually escape Earth's gravity well. And so when Earth was formed, plenty of helium around, but all of it has escaped into space, except for helium that's trapped in underground caverns and, as part of rocks or in spaces that don't have access to the atmosphere, so therefore can escape. So what that really means is that we have a limited supply of helium on Earth. Now, if you go to another planet, say for instance Mars, what do you know about the atmosphere of Mars? Yeah, it's mostly carbon dioxide, and one of the reasons is that if you take a look at it, the escape velocity on Mars has less gravity than Earth, and so there's no oxygen present on Mars because most of the oxygen is escaped. And I shouldn't say there's no oxygen, there's a lot less oxygen. And so Mars' atmosphere is mostly carbon dioxide because it's heavy enough to not have escaped from Mars' gravitational field. If you go to the moon, there's almost no atmosphere on the moon because all of the gas particles can achieve escape velocity and over billions of years have escaped from the planet's gravity well. And so in order for an atmosphere that sustains life to exist on Earth, it takes a very special set of circumstances, meaning the Earth has to be a very specific size with a very specific gravity. If you have too big of a planet or too small of a planet potentially, you won't have the right concentrations that we find for oxygen to have life. Now we know that life can exist without oxygen, we just know that it seems that a lot more of it exists when there's plenty of oxygen around. Okay, the next thing I want to talk about is diffusion versus something called effusion. And the words have two different meanings, but commonly, if you're not a chemist or someone that cares about it or is in this field, then we really tend to use them the same. What diffusion says is that it's the process by which gases mix, so process mix due to random molecular motion. And if you want to think about it, that's what happens when you open a bottle of perfume. The gases start to mix perfectly and the gas diffuses throughout the room. Diffusion is actually technically the escape of gases through a small hole into a vacuum. Oops. So a lot of times people will talk about the process of diffusion, and really they might mean effusion, or quite often it's the reverse. People are talking about a fusion and they call it diffusion. But the key here is that for a fusion to occur, you have to be going into a vacuum. And what it's really saying is that you've got a container. Actually, let me draw it in the right spot. So if I have a container like this, and I have a small hole in it, and I've got molecules A and B here, and I open it up to another molecule, a container that only has A's, what you'll notice is that eventually the molecules of B go through that, but the molecules are going both directions. If I'm talking about a fusion, what I really have is a container, and on one side it can be filled with A and B or whatever we want, but this side is a vacuum. And so eventually the A and the B molecules will diffuse, or technically, see, I should use the word effuse because we're talking about a vacuum, from one side of that container to the other side of the container. And we have the person that sort of discovered this. It's called Graham's Law. I always want to call it the graham cracker law. And what he says is that the rate of effusion is inversely proportional, so 1 over the square root of the mass. And he discovered this, and I don't know what year, but this is, I have, 1805. I was like, wow, he only lived like 15 years and came up with this? No, 1805 to 1869, so he lived to be 64 years old. And this makes sense if we assume, this makes sense based on kinetic molecular theory, KMT, because we know that U is equal to the square root of 3RT all over M NA. And so we know that the rate of diffusion is proportional to the speed, or the average speed. And so what it means is that we can write a law, and whether we write it as the average speed of 1 over 2 is equal to the square root of m2 all over the square root of m1. Please notice the 1's and the 2's are flipped because it's inversely proportional. Or we can write the same thing as u1 times the square root of m1 equals v2 all over the square root of m2, and sort of make it look like Boyle's law. And what this really means, and why it's important, and maybe why it's in the book, other than it's a good example of something, is that we can separate mixtures of gases by effusion. And the reason that this is important is that the most common use for this, and I won't say most common use, but the one that's I would say is the most important, is that we know that uranium-235 is only 0.27% of all uranium, And uranium-238 is 99.28% of all uranium. And that the one that we care about is the uranium-235. That's the one that makes us go boom if we make a nuclear bomb. And so, because the molecular weights are essentially the same, and chemically they're identical, it's very hard to separate them. And even by using this process of diffusion, it's also very hard to separate them. And so what they really end up doing is they react it with to form UF6, which is a gas. And then if you take a look at the ratio of uranium-235 to uranium-238, oops, got the U on the wrong side. This is a U for uranium. We know that the ratio that's going to happen is equal to the square root of their molecular weights, so 352.04 versus 349.03. And that means that if I do an diffusion process, that I can enrich the gas in uranium-235. That's where that term uranium enrichment comes from. And the way they do this is they make this gas that's a mixture. They take a centrifuge and they spin it rapidly. The heavier gas goes to the bottom of the centrifuge, the lighter gas goes to the top. And if you do this thousands upon thousands of times, you can eventually get a sample that's pure uranium-235 versus uranium-238. And the reason this is important is because making a nuclear bomb is trivial. If you gave me uranium-235, I'm pretty sure with the stuff laying around this room, plus maybe a little TNT or something explosive like that, I could probably craft a nuclear bomb. The hard part is getting the uranium-235 purified. Do you remember way back, I don't know if this is way back, within the last 10 years I think, there was a virus called the Stuxnet virus that went around computer systems. And no one could figure out what it did until they finally realized that it was a virus specifically written to interact with one type of centrifuge that the country of Iran was using to try to purify uranium-235 for their nuclear weapons program. Now, whether they have a nuclear weapons program or they're using that uranium for peaceful nuclear energy means, that's up to politics to decide. I'm not going to voice my opinion on that because it's really irrelevant. But the idea is that we crashed all of their centrifuges, or we didn't really crash them. We made them spin at such a rate, just a tiny little difference, not visible, not detectable really, that they couldn't separate the uranium-235 from the uranium-238 to make the enriched material for either nuclear reactors or for making nuclear bombs. So this computer virus was written solely to do one thing, which is to make making nuclear weapons difficult. That was its only goal. On all other computer systems, it just sat there and propagated and did nothing else, until it interacted with a computer that was controlling those centrifuges. And people think that probably the United States or Israel wrote it because they're the ones most concerned with Iran making a nuclear bomb, and so they get stuck with the blame. But I think it's kind of interesting, if nothing else, because we should realize that making nuclear weapons isn't hard. Or I shouldn't say making nuclear weapons isn't hard. Making the bomb itself is pretty easy once you figure out how to get the uranium or the plutonium. It's getting the uranium and getting the plutonium in a purified state that's actually the hard part. So I find it interesting. I mean, there was this big stir about 30 or 40 years ago. Some kid actually built a small atomic reactor in his garage by taking the radioactive material from thousands of fire alarms, scraping it off, and technically making a working nuclear reactor. Now, would he be able to do that normally? No. Was he able to make a bomb out of it? No. The material was too small. There's no way he could get critical mass. Plus, it was the wrong isotope for doing things. But the idea is that it's not hard to make these things. It's just hard to get the fuel for them. And so, if we want, we can make a nuclear reactor after class. No, just kidding. So that's about our time. So this should be enough to get you through homework, I think 9B. Oops, D, not B. And that leaves us one homework left and one thing left, which means that tomorrow's lecture will be really short. And actually, you can get through the first half of 9E. And so we'll finish up with the idea of ideal gases versus real gases on Tuesday. So for the rest of the week, what it's looking like is Tuesday, Wednesday, Thursday, Friday. Thursday, we're going to have an exam over chapters 9 and 10. On Tuesday, we're going to finish chapter 10. And then Wednesday, we're just going to start reviewing. And it's up to you guys what we review. We're either going to review for the test, chapter 9 and 10, or we'll start reviewing for the final exam, which is the following week. And your final exam next week on Monday and Tuesday is going to be over chapters 1 through, oh, let's see, where do we want to break it up? 1 through 5 or 1 through 4? I think we'll do 1 through 4 and chapters 5 through 10. And I'm trying to think, should I stop it at chapter? I think chapter 5 is not a horrible spot to include on the first half. And I should just check my finals from previous years and see how I divided it up. I just can't remember where I broke it up. So we'll do this. So it's either what chapters 1 through 5, or 1 through 4 or 5, and then 5 through 6, or 5 or 6 through 10. And if you remind me, I'll go look at my copy of the final exam and see how I usually do it. So work on your homework. Bring any questions that you have on Tuesday and Wednesday, and like I said, we'll finish up that last little bit on Tuesday. The last little bit on Tuesday is a little bit of theory and a little bit of math. So the math part, I figure you guys can do okay, and the theory part, it's only 2 little pieces to add to the puzzle, and so it won't be too bad. And that's it for today.